Yeah, sure.
And yeah, why don't we get going? We're at 10:30 and we've got a fantastic session ahead of us. We've got 4 speakers in speaking order: Kristian, Camilleri, Sophie, Ritson, Kevin Orrman-Rossiter, and Anant Tanna, speaking on histories and philosophies of physics. I will start with an acknowledgement of country. This virtual conference is being hosted from the University of Wollongong on Darawal, Yuin and Wadi Wadi land. And speakers today will be coming from the lands of the Wurundjeri, upon which a number of us are gathered in person, and also Bunurong. Kevin Orrman-Rossiter was in the room with us, but decided that he was going to go home to present from home. So he'll be joining on shortly, I'm sure. You know, sort of with that, obviously the theme of today of this session is different perspectives on studies of physics, and I will throw immediately to our first speaker, Kristian Camilleri.
Thanks, Martin. Am I still muted or am I okay? Can everyone hear me? I'm good. Okay. Just wasn't sure there for a moment. Let me hit, that's better. Okay. So let's begin. I'm going to tell a little story today about David Bohm's theory, his 1952 theory. I'll give you a little bit of an introduction to that. I'm going to not talk about the genesis of the theory itself, but I'm going to talk about its revival. So in 1951, David Bohm did the impossible, at least by John Bell's lights, when he developed a fully deterministic theory of quantum mechanics in which particles behave a lot like classical particles, which they're not supposed to do in quantum mechanics, in moving along well-defined trajectories in space and time. This was, of course, deemed impossible for several decades after the development of quantum mechanics in the mid-1920s. In fact, there were all sorts of proofs to demonstrate that such a theory of the type that Bohm did manage to develop in the early 50s would be impossible in principle. An early version of this view of Bohm's work had dubbed the pilot wave theory, had actually been presented by a French physicist by the name of Louis de Broglie in 1927 and who he presented at the 1927 Solvay conference, but under withering critique from many of the participants there, de Broglie had abandoned it soon after. So Bohm, unaware of de Broglie's earlier work, formulated his theory in the 1950s. It, however, as you could imagine, given the orthodoxy at the time, was subjected to, again, another round of sharp criticism. But more importantly, it was probably just totally ignored, only to undergo something of a revival in the 1980s, where foundations and interpretations of quantum theory began to undergo a resurgence. And today it is, in fact, a thriving sort of subfield, a small one to be sure, but a subfield of physics. The core question I want to address in today's talk is what led to the revival of the theory. It did happen, as it were, under Bohm's auspices in the college at which he was working at the time, but it wasn't largely driven by him, as I hope to show you today. This is the abstract of Bohm's initial 1952 paper. As I said, it did attract some attention at the time. It was considered the best of a bad lot by many physicists working at the time in the 1950s. It was the best example of a heterodox view, but one, as I said, that most physicists dismissed. There are a whole lot of complex factors which affected the reception of Bohm's work. Although you can see he'd submitted it from Princeton at the time of its publication, when it finally came out, in January of 1952, he had to go into exile in Sao Paulo in Brazil due to the McCarthy witch hunts, which had seen him have to leave Princeton. There's a whole story I could tell about that, but that's not my focus today. Just to give you a sense of the conspiracy of silence that confronted Bohm's work when it was first published, we can take a few excerpts. Isaac Isidore Rabi, at a conference actually in Sao Paulo, at which Bohm was present, remarked, "I do not see how the causal interpretation," that by the way is Bohm's, and the name given to Bohm's interpretation, "gives us any line to work on other than the use of concepts of quantum theory." In other words, it did little for the practicing physicists. J. Robert Oppenheimer, after hearing a presentation from Max Dresden at the encouragement of many of his graduate students on Bohm's theory, Oppenheimer stood up and said, "If we cannot disprove Bohm, then we must agree to ignore him." Some years later, at the 1957 Colston Conference in Bristol, Fritz Bopp said Bohm's theory cannot be refuted because it produces all the known predictions and empirical predictions of non-relativistic quantum mechanics, but at the same time, we don't believe it. And so that is more or less the view that the sort of environment in which Bohm was working. And as you can imagine, dispirited, gradually Bohm retreated from his own work. Now, he didn't retreat from the pursuit of new interpretations and new foundational ideas. In fact, he began to entertain several new ideas almost immediately after his groundbreaking paper, now regarded as groundbreaking, but it languished in obscurity. And actually his preferred model, and this is not emphasized anywhere near as much as it ought to be, for much of the 1950s was a very different hydrodynamic model. And that was the theory he presented at the 57 Colston Symposium. And by that time, he'd well and truly abandoned any thought that his original 52 paper, the abstract of which I showed you just a few moments ago, was going to be anything like the final theory. In fact, by the 60s, Bohm had abandoned working on this altogether. In fact, in a book he published, his ode to Hegelian dialectics, as he later put it, Causality and Chance in Modern Physics, Bohm wrote the following: "The author's principal purpose in 1951 had not been to propose a definitive new theory, but was mainly to show with the aid of a concrete example that alternative interpretations of the quantum theory were in fact possible. Indeed, the theory in its original form, although completely consistent in a logical way, had many aspects which seemed quite artificial and unsatisfactory. Nevertheless, as artificial as some of these aspects were, it did seem that the theory could serve as a useful starting point for further developments, which it was hoped could modify and enrich it sufficiently to remove these unsatisfactory features." So that more or less was Bohm's attitude and direction. The 52 theory was, if you like, a scaffold on which one might build the new edifice, which he hoped would supplant the existing theory of quantum mechanics. But by the 60s, he'd even abandoned that view that the older theory could provide some scaffolding. And in fact, he'd moved on to all kinds of weird and wonderful new ideas involving algebraic topology, and various other inspirations formed the basis for, in effect, what would turn out to be a fairly fruitless long line of research. After a kind of complex pathway out of Brazil, in 61, Bohm ended up as Professor of Physics at Birkbeck College in London, where he was left to continue to work on his own, more or less, on the foundations of physics. Bohm was in Brazil for his, as I said, he had to leave Princeton for communist sympathies, but Birkbeck College was known to be somewhere where such ideas were welcomed. John Bernal, the famous historian of science, Marxist historian of science, and of course, even more famous biochemist, was then head of the physics department. And Eric Hobsbawm, the famous historian of 19th century Marxism, was also president of the college. And the practice there was to teach evening classes to a handful of students often, and lectures often took place in Bohm's office. Now, PhD students, the few that Bohm had, were expected to attend his regular advanced seminars. And these were quite an experience for young students. They were introduced to all kinds of weird and wonderful ideas, as I said, often things Bohm was working on himself, things like algebraic topology. But being of a philosophical mind, Bohm also introduced them and made them read philosophers like Aristotle and Hegel. Hegel was well known to be one of Bohm's favourites. He was in this tradition of the philosopher-physicist. I'm afraid that is my phone. Okay, these were enormously stimulating sessions. If we take the testimony of many of the physicists who attended, or the young graduate students who attended, but they were very hard to follow. And Bohm he had a very restless mind by all accounts, and would often introduce one new topic 1 week before moving on to another, before anyone had a chance to digest the very difficult proceedings of the previous session. PhD students were not given topics to work on and were expected to find their own way. This was simply Bohm's way of working. There was no discussion of hidden variables at the time, the causal interpretation that Bohm had worked on in the early 50s. In fact, it seems that Bohm actively tried to avoid any discussion of this. It seems to have been a bad sort of time of his life, and he didn't like revisiting it. Two of his doctoral students, the two Chris's, who form the centerpiece of the next part of my talk, Chris Philippidis and Chris Dewdney, only heard of Bohm's theory from other sources, somewhat embarrassingly. Philippidis only heard of Bohm's earlier paper at a conference in Vienna in 1972 on the history of physics, when someone approached him and asked him how Bohm was getting on with his causal interpretation. And Philippidis, of course, had to somewhat embarrassingly confess he'd never heard of the theory. Chris Dewdney came across it quite by accident in another book, in Frederick Belinfante's Survey of Hidden Variables Theory, published in '73 at a nearby bookshop. Both, of course, approached Bohm about this earlier work, but Bohm said it was pretty much a relic of the past, and he rarely, as I said, spoke about events of the 1950s. Things began to change a little bit in the mid-70s. In a talk in '76 given in Strasbourg, Chris Philippidis proposed a new explanation of a particular perplexing effect. This is known as the Aronov-Bohm effect. It had been proposed in 1959. Experimental confirmation of the effect was still not yet at hand, but it was based on a radically new notion of causality, or so was Philippidis' proposal to explain the effect. It's a deeply puzzling phenomenon. Many physicists denied that it was a real phenomenon, in which a charged particle, contrary to all expectations, could be affected by a nearby electromagnetic field, even when the region in which the particle was, the field strength was zero. And this just obviously in classical physics, and even in the rudimentary understanding of quantum theory that many physicists were operating with, this should be impossible. At this point, after the talk, Philippidis realized, having read Bohm's early paper, the one published in '52, that this concept that Bohm had introduced there, and which he had subsequently found most unsatisfactory, the quantum potential, was the thing I was after. And Philippidis understood that here was a completely new notion of causality. This quantum potential wouldn't transfer energy and momentum to a particle. It would guide the energy and momentum already located in the particle. And so it was a new form of causality. In fact, he likened it to Aristotle's notion of the formal cause, one of Aristotle's four causes, which he'd of course learned in discussions in Bohm's seminars. Now, the idea could only be developed further if one knew how this mysterious quantity, this quantum potential, behaved in very specific physical situations. And so Philippidis set out he decided that before he tackled the very complicated Aharonov-Bohm effect, which was, of course, the target of his interest, he would apply it to the classic double-slit interference experiment, which is one of the most iconic experiments demonstrating the wave-particle duality in quantum physics. And he thought he would try to make a detailed calculation of this effect, but using Bohm's theory and trying to work out how the quantum potential affected particles moving through these slits. This would be, in his view, an essential first step in where he wanted to take his work. Initially, the calculations were difficult and the results were too obscure to draw any definitive conclusions. And Philippides, rather than taking his work to Bohm, who was his supervisor, took it to the other professor who was then working fairly closely with Bohm at the time, Basil Hiley, because it was well known Bohm did not engage in mundane and tedious, lengthy calculations. Hiley was more prepared to do this. It was suggested that they use the computing facilities, which were made available in London. A number of colleges, I believe, had use of one of the big supercomputers there. And they enlisted the help of a friend, Bob Kay, who suggested using numerical calculations to compute this quantum potential using a computer. And Kay showed Philippides how to program in Fortran. And after some months of practicing and acquiring the necessary skills, he obtained the first plots of the quantum potential. You see, this is depicted here in the image, these valleys and ridges and plateaus. These were quite startling and would prove to be crucial in clarifying the concept of the quantum potential beyond the level at which even Bohm himself had understood it. And it was, in Philippides's view, and later in Bohm's, in fact, a beautiful example of this new kind of formal cause, in addition to efficient causality through normal fields. Okay, and this sort of image here is a picture of the computing center at Birkbeck, probably a little later than the period I'm dealing with. So this is probably in the early 80s as opposed to the 70s. And a number of further plots and calculations were made. Chris Dewdney was brought on board. He was still struggling to find a thesis topic, as most of Bohm's students often were, and he produced the first particle trajectories. These are the trajectories that particles would move in, having been influenced by this quantum potential. And lo and behold, you could produce all the interference effects, which had been, up until this point, thought to prohibit any trajectory description of the phenomena. But here you have trajectories moved in all sorts of odd shapes, producing the interference effects. And this was immediately recognized by Dewdney, Philippides, and even when they showed it to Bohm, astonished at what they were able to produce. This was one of the resounding triumphs for Bohm's old theory, which was now nearly 30 years old and, as I said, had languished in obscurity for much of that time. Philippides earlier this year conveyed to me that the paper on the Aharonov-Bohm effect, the second paper that was published on Bohm's work in this period, was the fruition of my work. Bohm recognized at that point that it provided a new insight into the theory, and following these developments, the causal interpretation went through a revival of interest and grew considerably beyond its original bounds. Peter Holland, who would go on to publish the first textbook on Bohmian theory, also credited Philippides with having been the initiator and driver of the Renaissance in the de Broglie-Bohm theory, as it would later be called, in Birkbeck in the 70s and 80s. No one had yet explored the role of the quantum potential as the causal mechanism at work in this theory in the context of specific problems, and in particular this classic two-slit experiment, the iconic example of wave-particle duality. Philippides produced the first computer-generated images for that experiment and wrote the first PhD on the theory at Birkbeck in 1980, connecting the quantum potential with the Aharonov-Bohm effect. These studies propelled Bohm's neglected 52 papers, it was actually a two-part paper, into the foreground again, and were the most significant work done at Birkbeck, in that they appear to have inspired Bohm to start working on the theory again, and much else at Birkbeck and beyond followed. In fact, collaboration with researchers working at the Institut Henri Poincaré in Paris were initiated, and many researchers crossed between Birkbeck and Paris. This is the paper that Philippides, Bohm and Kay wrote, in which you will find those plots that I showed you just a few moments ago. And after this point, we begin to see the selling of the theory. Chris Dewdney made a number of 16mm films in which he made moving images of particles moving through the quantum potential. And these had stunning effects when showed to conference audiences in the 1980s. They made an enormous impression and played a decisive role in the resurgence of interest in the theory. Dewdney recalled there would sometimes be an audible gasp from the audience as they saw these particles tunnel through the barrier. One physicist confided in Dewdney that if there is anything that would convince me that Bohm's theory was valid, it would be this. So here we see these technological visual resources put to good effect. And so from this point on, Bohm's theory became what I would call a working theory, insofar as it began to be applied to a range of ever-increasing complex phenomena. The Stern-Gerlach effect, quantum tunneling, and the EPR experiment, and even the development of a version of Bohmian quantum field theory in the 1990s. And it was clear to Dewdney that actually calculating the motions, performing the tedious calculations that Bohm himself was so reluctant to do, would be very informative. And they, in his and many other people's opinions, transformed the situation regarding the theory and stimulated a small cottage industry in making trajectory and potential calculations under different circumstances. You can see from about the late 70s, early 80s, a discernible rise in the number of citations of Bohm's 52 paper after the very lean period in the 50s and early 60s. I realise I'm running out of time, so I'm going to wrap this up. I want to make a few remarks. The full potential of the quantum potential as an explanatory concept only began to be realised some 30 years after Bohm had first proposed it. And this is not an unusual chain of events in the history of physics. Often the potential of theories cannot fully be realised and is not even fully understood, even by the theory's creators. And it requires different socio-epistemic context to bring the theory out into full light and to see its full potential. Bohm himself seized on this opportunity, had his say in the theory that he, of course, had first constructed back in the early 50s. His posthumously published Undivided Universe with Basil Hiley is a testament to this resurgence of interest, a rekindling of interest. So, as I say, the internal resources of a theory often can't be realised or even known without further effort. And in order to get further effort, you often need people with complementary temperaments and abilities. We often say theories have predictive or explanatory power, and that's of course true, but it's often theories that don't make these predictions silently by themselves. It's theorists that have to do. And so the point I'd like to stress as coming out of my story is that theories, in order to become working theories, and in this case to gain some acceptance in the community, must be inscribed within forms of theoretical practice. And this requires historically contingent socio-epistemic, and in my case, also technological conditions to be realised. Bohm himself didn't like to do that sort of thing, so it was left to others to bring the theory out into the light. This proved to be crucial in the conceptual development of the theory and in winning adherence to it. So there are two parts. And you see the emergence of a new socio-epistemic network in Birkbeck, Paris, and in other places. The transition from a theory to a working theory is a crucial and often neglected aspect of the dynamics of scientific change, and it's one that is all too often relegated to mere application. And so on that note, I'll finish up. Thanks.
Okay, thanks very much, Kristian. Wonderful presentation. Much better than my job as chairing, because I skipped over a few things. So I will very quickly retrospectively introduce Kristian as a senior lecturer in history and philosophy of science, absolute stalwart here. Has someone in the room, or is this me? There's a bit of echo. Stalwart of the department, who, as he says, you know, sort of found HPS in his, what was it, in his undergraduate years and never looked back, and is currently working on a book, Quantum Mechanics and Its Discontents. One thing particularly to note relevant to that session is that those direct quotes that Kristian used have not been cleared, so please do not share them on social media or you know, sort of elsewhere. But everything else in this session, we, you know, happy and encourage you to share. And if you do use Twitter, the hashtag is at ARPS21. So with that, do we have any questions? We've got a few minutes left for questions and comments, so I'll throw to the audience. And we've got Peter Evans.
Thanks very much, Kristian. That was super interesting. It's really interesting that you talk about Bohm thinking hydrodynamically, because it seems like recently there's kind of a repeating of history going on. Again, out of Paris, these series of experiments in the last 15 years for the hydrodynamic analogue of wave particle duality. These experiments are now being done in MIT as well. I was wondering whether you know much about that. I mean, at the moment, it looks like they're more inclined to support de Broglie's original interpretation, and there's slight differences between Bohm and de Broglie on that. But I'm wondering whether you know anything about that, or whether you can comment.
Thanks, Peter. I hope you can hear me.
Yeah, absolutely.
I think there's a little bit of reverberation in this room, but we'll get that. Yep, that should be good. Okay. Yeah, so the hydrodynamic interpretation actually long had a bit of a history in France, because that was the theory that Vigier, who came to work with Bohm for a little while, did work on. And in fact, it never really fully went away. Yes, it's never really fully went away. I can't tell you much about the recent work that's been done that I'm not across, but Bohm sporadically went back to the hydrodynamic interpretation. What I would say, and you know, now we have a splintering off and many interpretations. And in fact, de Broglie never went back to his pilot wave interpretation. When he came back in the 50s, he went for another theory again, which he called the theory of the double solution. So you had this splintering effect where everyone started working on their own pet interpretation. Bohm was the sort of mind who was happy to jump between different working theories, which is, in my view, one of the reasons why he never carried through his own program initiated in the early 50s. And the new generation of Bohmians, if I can call them that, in Birkbeck and in Paris, they were much more fixated on the original form of the theory and not the hydrodynamic model and not the stochastic model and not all the splinter sort of avenues that Bohm flipped between. He had this it's very hard to follow his publications because he flips between. He's obviously the sort of man that thinks of four things at the one time and can only pursue one at a time, but keeps the other ones in mind. And so I can't tell you much, Peter, but I can tell you that this generation of Bohmians actually got stuck into one of the theories, and that's probably one of the reasons for its success. I'd venture a guess that with the hydrodynamic model, that also happened. A small group of people, experimentally and theoretically, started working hard on one of these interpretations, and we're seeing some of the fruits of that in recent years.
Yeah, thank you.
But if there's no further questions or comments for Kristian, Martin jumping in. Okay, last question, Martin.
Can you hear me all right? Yeah. Yeah, so just want to know if any of these lines of investigation coming out of Bohm's theories, whether any of them have led to any novel predictions.
Let me.
Not from the Bohmian camp, Martin. It was always hoped. In fact, this is one of the reasons that Bohm actually stopped working on this theory. He wanted a theory that would make predictions that orthodox quantum mechanics didn't make. I couldn't go into that in this brief talk. There are hopes. I think recent work done by, it's not that recent anymore, but Anthony Valentini has predicted some a deviation from the initial probability distributions, but that's out of experimental reach at the moment. So it's the kind of prediction that's going to be extremely hard to check one way or another. So at the moment, they're running level pegging. If that, there are heaps of other problems with the Bohmian picture. I'm not here to sell it. It's just a historical story at this point. But I'll leave that because we are running out of time. We can have a chat later if you'd like, Martin.
Okay. Thanks. Thanks very much. Can everyone join me in thanking Kristian for a fantastic presentation? And with that, I am going to so our next speaker is Kevin Orrman-Rossiter. Kevin is a part-time PhD student at the School of Historical and Philosophical Studies at the University of Melbourne. PhD is a biography of positron and its antimatter siblings. Interest partly arising from original training, as so many of us seem to have done in physics. Kevin will be presenting on some of that work to us today. So I will hand over to Kevin.
Hopefully we've got the right screen.
That's great, thanks.
Good. Good morning, everyone. What I'm going to be talking about is some discovery events, perhaps quite different to what Sophie's just been talking about, because what I want to do is go back to 1950s physics, when big physics, big science was a little bit smaller than the Large Hadron Collider at CERN, and talk about how some of the neutral antiparticles were first, I'm hesitating to use the word discovered, but how they came into being, because these are rather events that are quite different to what you would normally understand as classic discovery. In addition, the things I'm talking about, I think actually are quite illuminating into how physics occurs in practice, rather than the school book presentations. And even though that's been a big subject in HBS for many years, I just thought I'd like to illustrate these things. And I've changed my topic of or changed the title a little bit to actually demonstrate some epistemic niggles that I found when the experimenters were carrying out the experiments. Things that they actually assumed or that they glossed over to get to their discovery result, which didn't become obvious for, in some cases, many years or even decades later on. So to bring this in, let me start by introducing you to some of the family of antiparticles, because they're not always familiar, or we all assume we know what they are from a nice standard model of physics. Back in 1932, a rather disgruntled postdoc called Carl Andelson made what I call a serendipitous discovery, one of those lovely ones where he was looking for something entirely different and came up with an image in his cloud chamber of an antiparticle, so an anti-electron. He was good enough to even label it as a positron, and then suggested we should relabel the electron the negatron. But Carl ended up getting a Nobel Prize for this in 1936, so only 4 years after his discovery event. But as anyone who's actually looked at the positron discovery knows that even though the experimentalists went, yes, that's a great discovery, almost within 6 months, it took some 4, 5, 6 years of theoretical development before everyone went, oh, we understand enough about the positron that we can situate it theoretically. And some of that was actually hampered by Paul Dirac's work, which had occurred earlier on, but he'd made a prediction about it, which nobody had picked up on, experimentally that is, that there should be antiparticles of electrons and protons. And so it was hampered by his view of it. But nonetheless, this is what you would call a nice, easy discovery. And in any textbook on nuclear physics, the picture I've put up the top here, which shows the positron coming in, it's a cosmic ray, but it is still coming in from the bottom of the screen, goes up through a lead shield, loses energy. And from this, this is what Anderson worked out, what the mass and the charge, and said, oh, this is an anti-electron. Moving forward to post-war physics, and this is called big physics, maybe still not in the same league as the Large Hadron Collider, but nonetheless big physics in the sense that in 1950s, the University of California was building what was going to be at the time, and was for some 8 years, the world's largest particle accelerator, the Bevatron. And they deliberately built the energy such that they could create through a proton colliding with a stationary proton, they had enough energy in that collision that they could actually hopefully create the antiparticle and particle pair of a proton and an antiproton. So it was whereas before we had a serendipitous discovery, this was a very deliberate discovery to look for a particle that had been predicted. It did go to plan, and there was actually a number of probably 3 or 4 different teams who had put time in on the Bevatron to do the same experiment, to look for the antiproton in slightly different ways. The Nobel Prize went to Owen Chamberlain and Emilio Segre, who were the leaders of this particular experimental group. But again, this was a slightly extended discovery event, even though they knew they were looking for it. And as soon as they'd shown their experimental results, everyone went, thank goodness, we can move on a little bit. The antiproton's been shown there. It wasn't actually until some 6 or 9 months later that they were really comfortable that they said they discovered it, when they could show an annihilation event where an antiproton annihilates, in this case in an emulsion film, against another proton and creates a nice shower of pions, to actually show that they had created an antiparticle. So there was a combination of discovery, and then they used the actual visual effect of an annihilation as the clincher for their work. So fairly, if you like, standard discovery stories. And what that introduced was actually the concept of antiparticles quite heavily into our modern day particle physics. And you know, I'm not actually saying anything new when I say that normal matter is composed of at the time was composed of protons, neutrons, electrons, and photons. There was an ever expanding zoo of particles seen in various particle accelerator work, as well as the rather mysterious neutrino, which was predicted to be part of radioactive decay, and then other particles that were being picked up in cosmic rays apart from the positron. So an antiparticle is something that's got the same mass, opposite but equal electrical charge to its normal matter equivalent, and it annihilates with its normal matter equivalent to create a whole lot of other lighter particles and photons. So for example, a positron and electron annihilate together and create two photons. One of the interesting things when we start talking about, which is my area of interest in this specific talk, is the neutral antiparticles, is you can't actually see them in detectors at the time particularly. You have to look for some interaction product that says, here was a neutral particle, here is the interaction that happened, and from this we interpret we saw it. And again, there was another very deep assumption, that was that the neutron as a particle acted like a charged particle. Okay, it did have a magnetic moment, so it should have its own antiparticle. So going into these experiments, there was an idea that the antineutron should exist, and hopefully if it did, it would fulfill some expectations from Dirac's theory. And there's also at the same time the idea that the neutrino should exist, which I'll get to in a second little bit of my talk. And that's what I'm also going to talk about, is looking for both those neutral particles in experiments. Now, again, 1950s were a long way off the nice standard models of particle physics with quarks, leptons, and bosons. And to Sophie's point, a reasonably easy and nicely explained picture of particle physics. So what I want to do is briefly look at how did anti-neutrals come into being. So at the Bevatron, there was again a number of proposals at the same time, once the antiproton had been shown, to actually produce anti-neutrons using the antiproton beam, which was really nice. And two in particular made their way. In 1956, a team led by Bruce Cork did a group of experiments, and that's a picture of the group there. As you can see, typical sort of, if I say physicists of the day, and there's lots of white males sitting around a bit of equipment, looking like they're doing something so that they can get a picture for hopefully their Nobel Prize speech later on. At the same time, there was an alternative group led by Janice Button, and a lot of her team were actually the same team who got awarded Nobel Prizes, who were part of the Nobel Prize winning team that actually discovered the antiproton. And what they were doing, and I've stated this is the reasoning behind what their experiments were. The observation of antiprotons produced in high energy nucleon-nucleon collisions, so creating a matter-antimatter pair out of a high energy collision, made them to believe that antineutrons are also created in such processes. But the process they're talking about is one called charge exchange, and that's from Button's paper published in 1957. And that was the key bit in both of their papers were, and I'm going to call it almost a throwaway line, that they were going to create antineutrons from antiproton beams in a process called charge exchange. One of the interesting things about it, if you look at all the papers and you try and find a reference to charge exchange processes, there is nothing. It's actually, again, that's why I called it a bit of a throwaway line. It's sort of a niggle that was sitting there, an epistemic niggle. What were they actually talking about when they thought they were going to do their experiments? The experiments look something like this. Now, this is from Cork's paper, and it's the discovery paper of the antineutron. So this is their charge exchange experiment. They have an incident antiproton beam, which in the year since Chamberlain and Segre have discovered the antiproton, they've gone from 15 antiprotons produced per hour up to a whopping 600 per hour. So they're talking about quite a big increase in protons coming in here. And their detector system was a scintillation cube, so a solid plastic scintillation cube, which when particles go through that are charged, gives you a shower of electrons off, a shower of light off, which you can then measure with photon multiplier tubes around it. Then they had a series of other scintillation, plastic scintillators again, that the beam would pass through, and including a lead scheme, such that they would then capture, hopefully, their antineutrons in this Cherenkov detector here. And again, that was designed that an antineutron would come in, annihilate with a neutron or a proton in the counter, and again give a shower of light to the photon multiplier tubes all around it. The magic, if I can call it, happened in this rather nice little cube labeled X. And that's where the charge exchange happened. Now, Cork's experiment was worded such that we are going to, using charge exchange, produce antineutrons and detect them in our detector. And it's almost a bit of experimenters regress. They didn't know whether their detector whether they were producing antineutrons to detect in the detector using this process. because there's not actually any theories around that certainly that I can find. And if someone comes up with it, I'd be really interested in charge exchange or what was going on. After they had made their discovery claim, Janice Button's experiments were run and published. And hers were worded in a slightly different way, because she acknowledged that with the discovery of the anti-neutron, they could do, and their experiment was set up in a very similar manner, except that rather than having a scintillation cube here, they had a whole series of targets. And what they did was measure charge exchange cross-sections, knowing that they should be able to measure an anti-neutron here. So they sort of reversed the logic of the experiment, saying, now that we know anti-neutrons exist, we're going to use this presence of these to actually measure the process that's going on to create them and try and come up with some physics around that. Janice continued with those experiments for quite a number of years, and various other people did, measuring charge exchange processes, which they still didn't have an adequate theory for. So let me just, so the 1950s concept of a charge exchange force was somewhat ambiguous, and Catherine Carson's written a very nice two article, 100-page discussion on the peculiar nature of charge exchange forces, which are used to describe basically what we now call the strong force, the nucleon force. But it was this idea that they were thinking of when they used charge exchange forces to create something where a proton and an antiproton collide and give off a neutron and an anti-neutron. That's what they were trying to do. And in the 1950s, there was a number of analogies in theoretical physics about what this was. And by the late 1950s, there was an understanding that charge exchange forces were something to do with an exchange in the nucleus of another particle. But at the time these experiments were going on, there wasn't actually an epistemic, they didn't actually understand or have a knowledge about what they were doing. And it wasn't until the 1960s that Janice Button, in one of her other papers, then published an idea of showing a nice little Feynman diagram of a proton and an antiproton coming up and an exchange of a positive pion. And then from that, they came out with the neutron and the anti-neutron. None of this actually made sense until probably the time of the Standard Model in the 1970s, where you could actually follow that and work out, oh, there's actually a whole lot of gluon interactions going on as the two particles get close together. Not only that, there's an internal exchange of W bosons, and there is an exchange of pions. But at the time, the conceptual basis of this, there was actually nothing that neither Cork nor Button's group could give a theoretical underpinning for the actual experiment they were going to do. So their statement of we're going to create antineutrons by charge exchange was really a leap of faith, and I call it a bit of an epistemic niggle, which is why I was doing that they thought would occur, but nobody had actually shown it. And then they would use that, then they would hopefully then discover a process in their detectors that would show up that an antineutron has been produced and that they could measure it. It wasn't until the story of antiprotons and charge exchanges goes on is quite interesting, because it wasn't for another year or so until 1958 that, and this is a very squiggly diagram, but if you follow it carefully, there is actually an antiproton which is coming in at the top here. Through charge exchange at this arrow, an antineutron is created, and then way down here, the antineutron annihilates and creates a pion shower, which was then seen as the, if you like, the visual proof that this has actually occurred. The interesting thing was that Segre showed this in his 1959 Nobel Prize speech, which he entitled Antinucleons, and so he was actually almost appropriating the anti-neutron experiments back into his group, which discovered the antiprotons. So there's a fairly, if you like, tense and interesting idea of what was discovered and who discovered it. And the anti-neutron, even though there's an accepted claim, and if you look for who discovered the anti-neutron in a physics textbook, it'll be Quark and his team in 1956 claimed it. But it wasn't really until this came up that everyone went, oh, this is actually part of our particle physics family now, our anti-particle physics family. So I want to quickly just go and look at the other anti-neutral particle that I'm currently looking at, and it's tied up in a rather interesting set of experiments by Rains and Cohen, who were looking for, and they called it the poltergeist particle, the neutrino, which most people will know is a fairly well-established story. It was proposed by Wolfgang Pauli in 1933 to explain a problem in beta decay. Enrico Fermi in the next year or so developed it into the theory of weak force. And so theoretically, the neutrino was accepted as part of particle physics, even though nobody had measured it and nobody had observed it or detected it. But it had rather an ambiguous identity, including a nearly 2-decade-long view that the neutrino and its antiparticle could be used to make up photons, and so that was the neutrino theory of light. There were two different theories, whether it was a Dirac particle, that is, or a Majorana particle, whether it actually the antineutrino and the neutrino were identical or not. By this stage, also in the 1950s, looking at pions, pi mesons, that they'd shown that there was perhaps a need for a neutral particle in those experiments as well. And Rains and Cohen, in the hubris or the excitement of post-war, post-Second War physics, realized that you could try and detect the neutrino as long as you had a very high source of them. The sun is an obvious one, but it's hard to switch on and switch off to see whether your detection's been successful. A nuclear bomb, which was quite popular by both Rains and Cohen, and they went down some way of actually thinking of how to set off a thermonuclear bomb and measuring the neutrino flux from that, or a reactor, and then tie all that together with what are actually quite sophisticated detectors, detectors that have now grown into the sort of things that you see at the Large Hadron Collider, but they were very sophisticated for the time. At the same time, a neutrino, antineutrino annihilation probability, just to reflect back on the fact that quite often in antimatter experiments, an annihilation event is one of the key clinchers for it. The calculations that were done around this time showed that the probability of one of those mutual annihilation events happening was something greater than the lifetime of the universe. So the successor of discovering a neutrino, or an antineutrino for that matter, couldn't hinge on an annihilation event. So in 1953, so Rains and Cohen did a number of experiments at different nuclear reactors in the States. The first one was done in Hartford. They did one very long run and came up with a set of results which they thought were reasonably satisfying, but weren't convincing that they discovered the neutrino. The paper was titled "The Detection of the Free Neutrino," and the thing that intrigued me about this paper was it's all talking about neutrino, and then there's actually a little postscript stuck at the bottom of it, which again is one of those great physics throwaway lines, and it just said, oh, look, we find it convenient, and that's my emphasis, to label the neutrino accompanying beta minus emission, so normal beta decay where an electron is given off, as an antineutrino, and that accompanying beta plus emission as a neutrino. That was all that was said. The paper then goes on to talk about neutrinos, the detection, and how that they're now going to go and develop better detectors and try and measure it measure neutrinos in a slightly different way. What I found fascinating from this was in 1956, they did more work at the Savannah River nuclear reactor. And there they used quite a sophisticated sandwich of scintillation counters and targets to produce what they then gleefully claimed was that they had discovered they had observed the neutrino. The paper was titled that, and I think it's a rather interesting thing is that their discovery claims were published simultaneously in Nature, a paper authored by Raines and Cohen called The Neutrino, and a paper in Science called The Discovery of the Neutrino, Observation of the Neutrino, and it was authored by Cohen and Raines. So they covered both their North American and their European and British market quite well by publishing quite interestingly dual papers. In the 1956 paper is the diagram on the left, which shows quite clearly they've got their neutrino from the reactor. This is the reaction they were looking for. The neutrino comes in and does an inverse beta decay. So it collides with a proton, creating a positron and a neutron. The positron annihilates. They get gamma rays coming off 180 degrees. And so they're looking for a coincident signal in the liquid scintillation detectors either side of their target. At the same time, a few microseconds later on, the neutron loses enough energy that it is captured by some cadmium salts which are put in the target, and that causes another shower of gamma rays which are measured also by the scintillator detector. So what they're doing is they're looking for a series of non-coincident events that occur a few microseconds apart, and they set up all their electronics quite nicely to discriminate between anything that wasn't in what they thought would be a reasonable time frame for neutrons to lose enough energy to get captured by the cadmium in the target. But the thing that was fascinated by, again, was the emphasis on the neutrino from the reactor. And their paper was hailed as the discovery of the neutrino. At no stage was an anti-neutrino mentioned, and this was, the 1956 paper was published. It was presented at the American Physical Society again as the neutrino discovery. It was published in Times and a whole lot of other interesting magazines to show that they'd finally discovered the elusive neutrino. In 1960, Raines and Cohen followed up all their experiments because there was a number of, and I'll call them, it's been pointed out by a number of authors, that there was a number of accounting problems with getting all the physics right and the cross sections right, and they then presented all their results in a much more coherent format in a 1960 paper, which was called, coincidentally, Antineutrinos from the Reactor. And here they've neatly changed basically the same diagram, except that they've now said what they're actually measuring was the antineutrino. So my interesting part of this was that how did they actually discriminate between whether they were looking at a neutrino or an antineutrino? And the convenient identity came down to a still not completely accepted conservation of lepton number idea, which was in existence in the early 1950s, but by the 1960s had been established as one of the conservation laws that couldn't be broken. So everyone was quite comfortable with it. So in beta decay, it was then established by 1960, and the paper that beta decay, we have an electron created, lepton number 1, and therefore the balance must be created by a lepton of -1, which is designated as an antineutrino. So the identity of whether Raines and Cohen were detecting a neutrino or an antineutrino as different to lots of the other antimatter experiments we've been talking about, was actually down to something they couldn't measure themselves at all, other than via accepting the lepton conservation law. And it was still, it was wasn't proposed in a formal form until 1953, and they were still the parity conservation ideas and whether it was held in all cases was still going on in the early 1960s. So I find it really quite interesting that at the time they were looking for the neutrino, they were not sure whether they were measuring an antineutrino, an antimatter particle, an antiparticle, or a matter particle. And today it's actually quite interesting that even though if you look at physics books, they will still talk about the neutrino detection experiments, the neutrino discovery. Popular science books tend to mention the neutrino discovery, leaving the neutrino as antineutrino. You know, it's sort of like it's some sort of difficult particle that they'd rather not talk about because it takes too much to explain. The interesting follow-up is that Raines was awarded a Nobel Prize in 1995, so 39 years after there was a great excitement by the physics community in 1956, acknowledging the neutrino discovery. Cohen had sadly died in 1975, so it wasn't that. But the 1988 Nobel Prize was awarded to researchers for a 1962 discovery, so post-dating the antineutrino discovery of muon neutrinos. And so there's sort of this reverse, everyone's uncomfortable about the neutrino discovery experiments a little bit, but not enough that it's accepted, but it wasn't actually recognized until much, much later. So what I like to just do is pull these together and go, so the experiments I'm talking about that produced antineutrons, and I use the verbs here quite carefully. They produced the antineutron, they detected an antineutrino. It relied very heavily on big science of the day, new instruments, the Bevatron, nuclear reactors, sophisticated multi-stage Cherenkov and scintillation detectors. So all really big stuff for the 1950s. So they were quite ingenious experiments. But in addition, they involved a necessary assumption in both cases, different assumptions, but partially developed theoretical ideas, charge exchange forces and lepton and baryon conservation laws, that they unquestionably, and I hesitate to use the word unquestionably, but I think it's necessary, they incorporated into their experimental outcomes in identifying the neutral antiparticles. And then it was almost we go back and then we confirm that what we did discover was those neutral antiparticles. So I'm going to leave it there with those thoughts.
Thanks, Kevin.
We'll end my slideshow and stop sharing.
We've slipped about 5 minutes behind. We started Kevin about 6 minutes behind, so we will try not to slip too much further behind. But if anyone's got a question or comment for Kevin, we can take that. Questions or comments there? Just more rounds of applause. Okay, and then we can always deal with them a bit later. I'm sure chance to catch up with Kevin, but so I might, so we don't slip too much further behind. Move on to our next and final for this session speaker, Anant Tanna. Anant is a physicist and a communicator. His physics PhD was in astrophysics, including supernova remnants, active galactic nuclei, and large deep survey for primordial neutral hydrogen. And communication interests include physics outreach, astronomy and physics outreach, and teaching. Over to you, Anant.
Thanks, Martin. Can everyone hear me okay? Yes, all right, great. Thanks to all the organizers as well for putting this conference together. I'm glad to be here to talk to you about a new idea for why a mover experiences less time. So before getting into the new idea, I'll just go over a very quick bit of history and a review of time dilation, which will lead us into a new concept of how matter moves through space and accumulates time. So back in around the year 1800, Thomas Young finds that light is a wave with his double slit experiment. And at the time, waves were known to be mechanical in nature, water waves, air waves, sound waves, so on and so forth. And so the question arose, what is the medium for the propagation of light? If light is a wave, it must be the excitation and oscillation of some sort of medium. And the proposed medium was the so-called luminiferous ether, the light-bearing ether, a strange thing with sort of bizarre properties, rather dichotomous properties, like being able to fill space everywhere, but also having extreme elasticity, and supposedly being stationary in space, which is interesting because it provides, or would have provided, an absolute frame of reference against which all motion in the universe could be gauged absolutely. And for decades, there were various attempts to detect this luminiferous ether, including the Michelson-Morley experiment, which utilized Earth's 30 kilometers per second orbital motion around the sun, and hence 30 kilometers per second through the ether. It utilized that relative ether wind to produce drag on the speed of light along two arms of an interferometer. So we've got monochromatic light being split into two half beams, which each travel along two perpendicular arms of this interferometer here, then get recombined and produce an interference pattern on a screen. So just a pattern of bright and dark fringes. And the idea here is that this parallel arm, parallel to the ether wind, this experiences more drag. The light along that arm experiences more drag and ultimately trails behind the beam of light that travels along the perpendicular arm. So the idea with this measurement is you rotate the interferometer by 90 degrees, you swap which arm of the interferometer has the trailing beam of light, and the result of that is a shift of the interference pattern. The fringes themselves on the screen will shift by an amount corresponding to 30 kilometers per second of Earth's motion through the ether. But famously, this experiment achieved a null result. There was no fringe shift of the magnitude required being detected. So the established scientists at the time start thinking, oh, the ether must be different to what we thought it was. But the young up-and-comers were more readily willing to abandon the ether idea. And one of those was Einstein, who said, essentially, let there be no ether, and then what? And he realizes through a series of thought experiments, like with this train here, he finds that the speed of light must be constant for all inertial observers, regardless of their relative motion to the source. So looking at this thought experiment here, he asks, if I'm on a train traveling at the speed of light, and I look at a mirror, will I see my reflection in the mirror? So there are, of course, two possible answers, yes and no. If not, this is actually a problem. Because what it means is that if you don't see your reflection, light must not be able to reach the mirror. So the speed of light relative to the train must be zero. And this allows the observer in the train to immediately deduce that the speed of their train, the speed of their inertial frame of reference, is v equals c. And this violates the principle of relativity, Galilean relativity, which finds that there is no preferred inertial frame of reference. All inertial frames of reference produce the same results for any given experiment. So you can't deduce your motion absolutely from within your own inertial frame. You can only gauge your motion relative to some other frame. So the answer of no, we can't see our reflection, can't be right, it violates relativity. The answer therefore must be less. And we measure the speed of light in the train, in our train carriage, to be the normal speed of light, as we would measure it in any other inertial frame of reference. So this satisfies the principle of relativity, but is a starkly different result or conclusion to what would have happened with the ether. So there's several consequences to this apparent constancy of the speed of light. One of them is that simultaneity becomes relative. So if people observe, if some observers see two events occur simultaneously, like two fireworks going off at the same time, Other observers will not necessarily see those events as simultaneous. They'll see one go off before the other. Now, all observers do agree that two events occurred, two fireworks went off, but they disagree on times and ultimately positions as well, which indicates the relativity of time and the relativity of space. Specifically, the predictions from special relativity are time dilation and length contraction, which are two equal and inverse changes to time and space, which leads us to the concept of 4D spacetime, where we describe the locations of events using these 4 coordinates that we have down here. So looking at time dilation, we can use a simple light clock here, which has an emitter, a mirror, and a detector. One tick of the clock, so to speak, is an emission of a light pulse, which travels up distance d, reflects down distance d, and is detected by the detector at the floor again. And in the frame of the train, in the rest frame of the train, what this observer measures is what we call proper time, right? Everyone measures their own proper time when they're in the rest frame of their own clock. So this proper time T0 corresponds to the distance traveled by the pulse of light and the speed of that pulse of light. But someone outside on the ground looking at the train moving past them at speed v, what they observe is the clock pulse, the light clock pulse in the train traveling a longer path. It's emitted here at the left, reflected off the mirror in the middle, and received at the detector on the right. So in the time that they see the train clock accumulate, for example, 15 seconds, what they've observed is light traveling at a constant speed over a longer path, and therefore taking a longer time to travel that path. So from the ground frame's perspective, when they look at this train clock moving past them, they observe it to be ticking slower than their own clock. Consequently, their identical clock on the ground, which they observe to be ticking at the normal rate of 1 second per second, they see their own rest frame clock accumulate more seconds than what they observe to accumulate on the moving train clock for the duration of that experiment. All right, so the ground frame observer looks at their own rest frame clock, sees it ticking at the supposedly normal rate of 1 second per second, and being a faster ticking clock compared to the train clock, it accumulates more ticks, more time. But due to the principle of Galilean relativity, the Galilean principle of relativity, there is no preferred inertial frame of reference. All inertial frames are equally valid. They all get the same result for the same experiment. So this time dilation effect is symmetrical. A person in the train watches the ground move past in the opposite direction at speed v. They observe the ground clock to accumulate 15 seconds with a light pulse that travels a longer distance and hence takes a longer time. And so they observe their own clock to be ticking faster at what they observe to be 1 second per second. So the question arises, whose time is actually slower? Whose clock is actually slower? Well, it's both. They each think the other's clock is slower than their own, and so they ultimately disagree. But this is fine because time is relative and all is well. And I won't spend too long on the maths here, but if we take the long path of the relatively moving clock's light pulse, we can do some maths, and we get this equation down here at the bottom right, which allows us to directly relate what larger elapsed time interval is measured by a rest frame observer when they compare it to the smaller elapsed time interval that appears to accumulate on the relatively moving clock. And what this tells us is that when the velocity, the relative velocity between the frames is 0, these two things are the same, all right? Because both observers are in the same rest frame with two clocks that are identical in their own rest frame. So they see both clocks ticking at 1 second per second. But as v approaches c, we find that the difference between t0 and t nu, the dilated time here, t nu, and the proper time t0, the difference between them increases, and quite dramatically so as v approaches the speed of light. For a very small t naught, we can end up with a very large t nu. And this type of effect, this time dilation effect, has been proven quite famously in the Hefele-Keating experiment, where synchronized atomic clocks were moved in 3 different ways. One was left on the ground, one was placed on a commercial jet aircraft and flown westward around the world, and the third was placed on an equivalent or identical commercial jet aircraft and flown eastward around the world. And what they found is that the eastward flying clock elapsed the least amount of time, the westward flying clock elapsed the most amount of time, and the ground clock measured something in between. So essentially what they found was that the slowest mover here, moving slowest relative to the center of the Earth, that slowest mover had the fastest ticking clock, accumulating the most amount of time, while the fastest relative mover, again, relative to the center of the Earth, the fastest mover had the slowest ticking clock, which then accumulated the least amount of time. So this is a direct confirmation of this sort of effect we see here, right? Where the faster mover does indeed accumulate less time, accumulate fewer seconds. But when this sort of, when the symmetry of Galilean relativity is misapplied, we end up with a little bit of physics fun with the so-called twin paradox, where people think there's a paradox regarding which twin ages less. So we've got a ground twin and a space twin. The ground twin likes to stay at home, the space twin likes to travel around. So the ground twin remains on Earth, and from their perspective, the space twin travels away from Earth at high speed to a distant star and returns at high speed, and when they meet up again, the space twin has aged less, the space twin being the mover from the ground twin's perspective. But when you apply the symmetry, you can think that the space twin sees the ground twin and Earth fly away at high speed, so there's an obvious problem there. They see the ground twin and Earth fly back at high speed, and the ground twin apparently ages less. So the so-called paradox is who actually ages less, but it's not really a paradox, because of course the Earth is not actually flying away at high speed. The Earth is not the frame that experiences a net force and moves through a non-inertial frame of reference of changing velocity. It is in fact the space twin who does move away and come back. So we can be sure, we can be confident that it is the space twin who is the mover in this situation. And we can look at it from a third frame's perspective. If we step back from these 2 frames, Earth and ground, and just watch them from a third frame out in space, let's imagine that the Earth does fly away at some high speed, and after a period of time, the space twin decides to catch up to the Earth. They wouldn't be able to catch up if they simply matched Earth's speed. That would only maintain the distance between them. So the space twin would have to travel even faster than the Earth to catch up to the Earth. Therefore, the space twin travels closer to the speed of light and experiences stronger time dilation effects than the ground twin, their twin on Earth. And so during or throughout the overall experiment, the entire experiment, because the space twin has traveled considerably closer to the speed of light for a given time, they end up aging less, right? So even from the third frame, when you do it right, it is the space twin that ages less. But the space twin, looking at their clock in their spaceship, they only ever measure their own proper time. Everyone measures their own proper time in their own frame, including the space twin, and yet when they arrive back at Earth, they have aged less than their Earth-based counterpart. And so the question I have is why? How? What is the underlying fundamental mechanism of motion through space that allows someone to age less than their twin on Earth while still experiencing and measuring their own proper time of 1 second per second. And it's from the desire to understand this that I'd like to present a new idea of how a mover experiences less time. Just a fun sort of thought process that I came up with back in 2013, 2014, while teaching introductory special relativity and introductory quantum mechanics to high school students. So let's consider space to be full of containers. The structure of space itself is a 3D grid of containers, much like the background of my lecture slides here. And a particle is a certain set of fluctuations in certain fields. So all the fields are everywhere all the time. But a particle, which is in a specific place in a specific time, that particle is a set of fluctuations. So for an electron, you'd have a fluctuation in the EM, the weak, and the Higgs fields, but not strong, because electrons don't experience the strong force as leptons. A quark would have fluctuations in all four, or all of the fields, since they feel all of the forces. So a system which is a set of particles, right? It could be a clock, it could be us, an observer. A system is a set of particles occupying a container or a set of containers. And within a container, a system can evolve. A clock can tick, we can experience the passage of time, we can accumulate seconds by being within a container. But as you move through space, the information that describes your particles and the state of you as a system, that information has to transfer from container to container, and the system cannot evolve during that transfer process. Because if it did, then the receiving container would receive something different to what departed from the previous container, and information would not be conserved. And we know that doesn't happen because when we move things around in space, we see that information is conserved, and we see that there are no skips or jumps in the evolution of a time evolving system. So we don't see a moving clock skip ticks, so to speak. But because a system doesn't evolve during the transfer process, you can't perceive it, right? Now, the way this relates to the time or the aging less of a fast mover compared to them measuring their own proper time is that at low speeds, you're not traversing containers particularly quickly. And so the majority of your existence is not spent in the transfer process, but is spent within containers where you can experience time, where you can evolve as a system and accumulate seconds on your clock. But at relativistic speeds of V getting close to C, you traverse containers very quickly, and so you end up spending a larger proportion of your existence in the transfer process, not evolving in time, not accumulating seconds on your clock. So when the observer goes through the transfer experience, or when the observer transfers the information describing their particles from container to container, the observer can't actually experience or perceive the transfer process because of whatever brain signals that move around, allowing thought and perception. This is a system that evolves in time, and during the transfer process, that doesn't evolve. There is no experience or progression of time in the transfer process. So an experiencer, an observer as an experiencer, isn't actually able to perceive the transfer process. An experiencer only ever perceives the time with which they are in a container, experiencing time, having their seconds accumulate on the clock. So the clock is the same. It only accumulates seconds when it's within a container, not during the transfer. And what we perceive is only the times when the clock is accumulating seconds. So to us, we're looking at our clock in our rest frame and we see it ticking at 1 second per second. But then if we're moving around at high velocity back and forth throughout the universe, we can end up aging less because we've spent a large fraction of our existence not accumulating time on our clocks because we were spending a large proportion of our existence in the transfer process. So we can do more fun stuff with this space containers idea. We can say that if the transfer process for mass is a bit slower than for non-mass particles, with the Higgs field coupling forcing some longer duration transfer process, then we can give us a reason why the velocity of mass is limited to less than c, while the velocity of non-mass particles like photons is the speed of light. And we can modify this idea a little bit to give us a reason for length contraction and mass dilation. If we say that the transfer of mass information into a container previously containing mass information is faster than when you transfer mass information into a previously empty container, then this allows the back of a spaceship to catch up to the front, because the back is moving into containers that previously hosted mass information, while the front is ostensibly moving into empty containers, a vacuum. So the back catches up to the front. You, as the experiencer within that set of containers, measure the proper length of your spacecraft, because you yourself are also being compressed or contracted. And you can end up with mass dilation as well, because you have a given entity, the spacecraft, occupying a smaller number of containers. So more mass per container gives you this mass dilation effect as you approach the speed of light. But there's also the question of why light itself is limited in speed. If it doesn't have mass, why does it travel at speed c instead of anything more? Which leads to the concept that there must be some minimum amount of time to spend in a container. There must be some quantum of time that defines the fastest interaction that can occur. And these very short, sequentially occurring quanta of time allow interactions in space to occur smoothly. We watch time evolving systems evolve smoothly in time, as opposed to jerkily or in a stepwise fashion. And these quanta of time are essentially timestamps on containers. They happen regardless of anything moving through the container or experiencing time within a container. They're always there, just sort of ticking over. It's the way time happens in the universe. And we experience time as these quanta of time tick over when we're in a container, but not during the transfer process, where we are essentially paused. So the question is, of course, what is a quantum of time? How long is it? Is it 10 to the minus 40 seconds? Is it a Planck time? Is it 10 to the minus 20? We would need extremely high time resolution devices and equipment to be able to try and detect this quantum of time. Of course, if the quantum of time limits the way the machine itself works, then it may not even be detectable. But if it were, for example, let's pretend we can have an arbitrarily high time resolution measuring device. If we had one electron, electron 1, electron 2, if we pushed electron 1 toward electron 2, then there would be a disturbance in the EM field. That information, EM field information, propagates from electron 1 to electron 2. And there would be a time delay between the receiving of the EM field information by electron 2 and the reaction of electron 2. Essentially a one quantum of time delay between the reception of the EM field information and the repulsion of the second electron. Of course, to have any hope to try and measure anything like this experiment, we need better clocks and circuits, well, basically better everything, right? So it's definitely a future experiment, not something we can do right now. And just to wrap up, I'll finish with this slide here, where we can use this space container idea to do some general relativistic fun as well. For example, a warped spacetime is warped containers, where the presence of mass distorts the shape and distribution of these containers, and this allows us to then invoke the observed general relativistic effects that we've already found and seen, things like gravitational lensing, the torsional shear of spacetime around a rotating mass, which was confirmed by Gravity Probe B. And we can encounter things like gravitational time dilation, where moving around deep inside a gravity well requires container transitions more often than moving around higher up in a gravity well. And so the mover deep in the well experiences stronger time dilation effects because of the compressed containers that they're moving through. They spend they spend a larger proportion of their existence in the paused state in the transfer process. And then there's other fun things as well, like black holes. Black holes function as per normal, but the question of the singularity remains. What is a singularity? Can space containers merge under extreme gravitational pressure? Or is there some sort of space container degeneracy pressure that holds up a singularity and prevents it from collapsing even further? And then, of course, there is the question, how big is a space container anyway? And that's the question I'd like to leave us with. My opinion is that time will tell. So thanks very much.
Thank you, Anant. Very thought-provoking, a lot to think about there. If you want to take your slides down, we'll see if there's questions and comments from the audience. And Martin has a question there.
Thanks for that. Can you hear me all right?
I can.
So yeah, I just wondering if you're familiar with
You're a little soft, Martin, if you try and right into the microphone there.
oh yeah, okay. I just wondering if you're aware of work by Stephen Wolfram on cellular automata, for example, in a new kind of science, and where it's got a similar idea that where you're breaking up space into cells and time into discrete units, and he derives this time dilation from that technique in a similar way to you doing, just using classical, non-relativistic assumptions. He gets this kind of result.
I have to admit, I haven't done any reading on the topic. It's just something, a fun sort of thought process that I've sort of been kicking around just in my head for a while. And one of my friends said, hey, why don't you present at this conference? And I thought, yeah, sure, why not? So I haven't really tried to look for any sort of historical motivations similar to my own ideas, but I'm very much keen on looking into it more. So could you just say the name of this this individual again? Something Wolfram?
Stephen Wolfram, yeah. I'll write it in the chat as well.
Great. That'd be great. Thanks.
And Kristian, probably see us through.
Can you hear me?
Yes, I can hear you.
Yes. Okay, great. Thank you. I have a couple of related questions. At a few occasions, you said spend a greater proportion of their existence, and I could tell you had to stop yourself saying a greater proportion of their time in cells or in transfer. So I guess it raises a question: what do you mean then, greater proportion of their existence, or equal proportion, or less? And second, are the cells contiguous? Are they right next to each other, or are they in some sense separated? So what I'm trying to get to with my questions in not a very eloquent way is, what do you actually mean by transfer? I know you mean from container to container, but if we can't measure the separation in space or in time, in what sense is there a transfer process, to use your terminology, at all?
On mute. Right. So the space between the containers isn't really a space. It's not a place where, physical dimensions X, Y, Z would be experienced, or where the fourth dimension time would be experienced. What it is it's sort of an intermediary between these containers, which are contiguous. I don't see a reason why they shouldn't be. But it's a mechanism invoked to help explain why the space twin measures their own proper time while aging less. That's all it is. And in regards to your first question, what does it mean for someone to spend a larger proportion of their existence experiencing time or not experiencing time? Well, because the experience of time depends on being in a container, but you can spend part of your existence not evolving in time, we have to make the distinction between what is the overall existence of a system, an entity, and the experience of time. So if you say, for example, that 90% of someone's existence is spent in the transfer process, then only 10% of their existence is spent experiencing time. But all of their time spent experiencing time is spent within the container, evolving in time, perceiving time, accumulating seconds on the clock. Does that make sense? Sort of, maybe? All right.
Since you've got the microphone.
Hi, can everyone hear me okay?
Yes.
So, I mean, I guess my question is, you mentioned this is sort of developed as a sort of pedagogical tool. And I guess my question is, do you have any specific pedagogical challenges in mind that this sort of mental model would help students alleviate? So are there any specific ideas surrounding relativity that this model would elucidate in a particularly vivid way, or anything like that?
Well, that wasn't really the motivation for this model. It was more of a personal desire to understand something that I basically raised as a question to my students when teaching them intro, special rel, and quantum mechanics. It wasn't something particularly that I intended to use as a tool to help alleviate misconceptions or misunderstandings or difficulties in achieving understanding. I feel like if I threw this at a bunch of high school students, it would make their lives harder, not easier. So it's never been used in teaching. But the question in my mind did arise as a consequence of teaching. If it were to be useful to help students understand special relativistic effects, or even general relativistic effects or quantum mechanical effects, then that would be great. But I think that as an idea, it would need more work before it would become a useful tool to teach to high schoolers, or to use in teaching high schoolers physics, or undergraduate students physics of special relativity.
Thanks very much. We've now run 10 minutes over time, so we've gone through a lot, but you know, we all need breaks soon, so we might wrap this to a close. But can everyone that's still here join me in thanking Anant for the presentation? So we'll take a break now. Sessions resume again at 1:30. There is the One2Me social space that you can go and chat to people one-on-one in during the lunch break if you like. There's also a postgraduate event, of course, running at the moment, which I commend it to you, but we will see you all later this afternoon. Thanks very much. Oh, and thanks especially to Brittany for her fantastic assistance on tech support for the session. It's been so good. Thanks.